Alrighty, so here we go. This is a heat transfer problem of the thermal conductivity through a pane of glass. I'll let you go ahead and read this question here. Just go ahead and pause the video and read it. We won't be doing the second part, so starting from here and almost to the end with the air in between the glass, we're not going to do that part because it's identical to the first part. So just go ahead and read that and see what we're doing. I'm going to go ahead and jump right into it here. Okay. So, first thing you want to do is kind of draw a picture so you know what you're doing. So, we've got a pane of glass of this thickness, which is actually going to be 5 millimeters. And then we know that it has a height, well, like this. It has a, excuse me, what was the height on that? It has a width of 1 meter and a height of 2 meters. So, we've got those two labeled right there. We know that the thermal conductivity of the glass, which is K, is equal to 1.4 watts per meter Kelvin. And then we know that the T on this side is equal to, we're going to call this one T1, is equal to 15 degrees C. And then the temperature on this other side, on the surface of the pane of glass, is T2, which is equal to negative 20 degrees C. So you can say outside, inside, or whatever, however you want to label these T's, it doesn't really matter. Alrighty, so then moving on from that, we know that to figure out the rate of heat transfer through a certain piece of glass or some material, we're going to use the equation for Q. Q is the rate of heat transfer through a surface. This is actually called Fourier's law. Now, okay, and the equation is kg times the area of T1 minus T2 all over L. Okay, and this T1 minus T2, this is actually just delta T. So basically, you take whichever temperature is highest and subtract whichever temperature is smallest from it. So T1 and T2 are interchangeable. Within this, I could change this one to T1 and make this one T2, and then you'd reverse this little situation up here, and then you just have to realize that heat always moves from the hottest side to the coldest side. So our Q is going that direction, just like that. Alrighty, the area in this equation is the area that the heat is moving through. So sometimes later in heat transfer, there'll be several different areas that you work with. You have to remember that if Q is moving from this side to this side, the area is all of this stuff right here. So that's the area you deal with. You never deal with these side areas or anything else, especially when you're working with conduction. So going ahead and doing this, we have 1.4 watts per meter Kelvin times an area, which is 1 meter times 2 meters, which is the area of the window. And then we've got T1, which is 15 degrees C, and minus negative 20 degrees C, all over L, and L is the thickness right here. So that's a little bit confusing because you think of L as length, but if you want to, you can change that L to like thickness and just remember that in this equation. It would be a slightly easier way of looking at it, but if you get confused by this, you can imagine L also as, imagine if you had a cylinder that's perfectly insulated and you have heat going through it like this. Then L makes a little more sense because it's the width of stuff that you're actually moving through, how much material you have to go through. So now this is 0.005 meters. Alright, you may notice that we have a Kelvin down here and we're doing these in degrees C. Since this is a difference of temperature, a difference in Kelvin is the same, or a difference in Celsius is the same as a difference in Kelvin. So you don't have to convert the Celsius into Kelvin if you don't want to. It is a little bit nicer because it keeps it very clear of what you're doing and you don't ever have to worry about units. But if you just remember that a difference of Celsius is the same as a difference in Kelvin, you can just ignore that and you'll know that these are going to cancel. So going ahead and doing that math, you're going to end up with 19.6 watts moving through this area of window. And that's all you do. You just take the numbers that you've got in the equation and you plug them into the equation, and that's all you got. So If you were actually doing it for the cylinder over here, just for another example, the area would become the area of the circle, and like I said, L would become the length of that. So if this was like a metal rod that you're heating one side and getting heat from the other side, that's how you would do that. But everything else would remain the same. It would have its own coefficient of conductivity and so on and so forth.